I guess one of the yeah. So
Alrighty, howdy everyone. We'll get started. Welcome to another week of review session stuff. In terms of announcements, your first exam is next week. It's in 8 or 9 days, depending on what class you're in. Next week I'll have a Zoom review session, probably like late, like 8 p.m. late. Tuesday for about an hour, hour and a half, and then we can extend this session on Wednesday a little bit later too, so you can answer all of your questions. But that will be the 2 review sessions that I'll have for next week, and then I'll be available Thursday and Friday by email if you have any questions. But just look for an announcement probably Monday of when that is going to be in terms of the Zoom, and then I'll send the Zoom link along with that announcement as well. And then be on the lookout for a practice exam from your professor. They are providing those. I highly recommend doing them. Those are usually pretty good practice questions in terms of preparing you for the exam. That doesn't mean if it's super easy and you can do all of them that you're gonna get a 100. But just that's a good starting point in terms of like content that they're going to cover. And then I'll post some extra practice problems as well once the mock exam comes out, that it will kind of be similar to the questions on the mock exam, so that you get even more practice before your exam next week. Any questions on that?
Do you know when our quiz grades will come out?
Friday. Yep. Any other questions? Alrighty. What do we want to see today? What questions do we have so far?
Well, I think go over what's covered, like, Monday, Wednesday, and then do you know, like, the stuff that was covered on the quiz? Because I know I didn't, you know, me early on.
Mhm.
Only group me a lot.
I can kind of see what was on the quiz, but I know that there's still some people taking it, so I don't think we can discuss the quiz until like next week. Yeah, and then like once grades are released, then we can start talking about that and what was covered on the quiz. Okay, any specific questions from the start of the week?
I know we didn't like lecture about pressure yet. I know I was ahead. I just think we can cover some of that.
Yeah, absolutely. Anything else? Okay, we'll do a quick little brief on gas laws, and then we can talk about partial pressures and all that fun stuff. So, we have our gas laws. Mhm. And can someone tell me a gas law that they know that we covered? We have Avogadro's. And what is that one? Or what does it relate? Yep. What else do we have? Yep.
I'd like to know the name of it or just how to apply it.
Know how to apply it. Yep. For lab, right, they might be like, oh, this is a Boyle's law, gas law kind of thing. So if you're given Boyle's law, you should know what the relationship between those
Yeah,
are.
but we've never done it.
On a test, no, nope. What else? What does that one relate? Pressure and volume. We do relate volume and temperature. But what is that one? Good. Charles. What kind of relationship does moles and volume have? This is a direct relationship. What about pressure and volume? This is inverse. And what about volume and temperature? This is also direct. What is the gas law that combines all of these? Good. And do we know what that's called? Yep, the ideal gas law. This is PV is equal to nRT, or as I will probably refer to it as PIV nert. Just more fun to say. Okay, and in this you have pressure and volume is equal to number of moles. What is R here? It's a universal gas constant. And then we're relating temperature. Does anyone know what the universal gas constant is? 0.0821 or 0.08206. Either one's gonna give you the right answer. I have learned it as 0.206, so I'll probably use that more often than not. But 0.21 is great. Does anyone know the units?
Like each one liters.
No.
Yeah.
All the ones.
Perfect. Yep. So, right, R is being multiplied directly by moles and temperature. So if that is all being multiplied together, that means that we need to divide those units out. So the universal gas constant will always be divided by moles times Kelvin, right? Your mole unit and your temperature unit. And then that means that if you were to divide by R, right, then your PV is going to be divided by R. So you need to have your pressure and volume unit on top. And someone did say it is liters times atmospheres. Right, so it is super, super important that when you're using the ideal gas law, that all of your units match the units of the R constant. So you want your pressure to be in liters, right? If you're given milliliters, you need liters. I'm sorry, your volume needs to be in liters. Your pressure needs to be in atmospheres. So if you're given millimeters of mercury, if you're given kilopascals, right, that all needs to be converted to atmospheres before you can use it in the ideal gas law. And then you just want moles in Kelvin. So the big one here for moles in Kelvin is temperature. Temperature will never be in Celsius. You always have to convert your temperature into Kelvin. You can change the units on R, right? You can, instead of converting the value you're given, you can convert the value of R, but I would recommend just changing your pressure or volume for that one. Any questions on R? You may or may not be given this. You should use it enough where you kind of recognize it. R does have two values. So if it is on your reference sheet, it'll probably be given to you as this version here. It'll also be given to you as 8.314, but that has different units. So make sure you're using the correct one with the correct units. Alrighty, any questions?
Liters times eight, times atmospheres over mole times, kilopascals.
Yep.
So, do we need to know any of the science behind why all those different types of units, or we just need to know the correct?
So technically, no. Right, the big point behind that is that you can have P1 V1 divided by N1 and T1, and that's going to be equal to the constant R. So if you change the pressure, volume, anything like that, you can have P2 V2 over N2 T2, right? Those will always equal R together. So whatever changes comes out to be R in terms of standard temperature and pressure. You don't need to know why that is. You just need to know that R exists. And then you need to know the relationship between all of these other variables. So looking at just PV and T is equal to R. This here on the left-hand side gives you all of your relationships that we talked about at the top of this page, right? You have pressure and volume for your Boyle's law here. And we can see that they are being multiplied together, which means that they have an indirect relationship or an inverse relationship. So if pressure goes up, what does volume have to do? It has to go down in order to stay constant with that R. You also have volume and temperature for your Charles law. These are being divided, so they have a direct relationship. So if volume goes up, what does temperature have to do? It also has to go up, okay? And then we also have your volume in moles for Avogadro's. Right, and if we're putting more moles into the system, what happens to our volume? our volume is also going to increase, right? So though, again, has a direct relationship. If one goes up, the other goes up. If one goes down, the other goes down. Right, this is important if we just have a random question that says, you know, pressure was doubled, volume was doubled, moles stay the same, what happens, right? You need to make sure that you're able to look at those and just kind of blanket statement, see the relationship between them. Right, and then you don't have to memorize all the individual gas laws that we talked about first, because they're always in the ideal gas law, and the ideal gas law is always going to be given to you. But I think you'll memorize PIV-NERT very early on, so you don't need to worry too much about it. Yep.
These are related pressure and temp, do they not have any sort of relation that we need to worry about?
They do, right? If your temperature goes up, then your pressure goes up. Right, if you think about it, there's just no, yeah, there might be one, but we don't really care about it, yeah. But you can think about pressure and temperature as if you're trying to boil water. Does your water boil faster if your lid is on your pot or off of your pot? On, right? And why does that happen? You have in a closed system, right? You're going to create that pressure faster, and you're going to find equilibrium between the pressure, and that's why your water heats up faster. So if you're waiting to boil water, put a top on it. Any other questions? And what would pressure and temperature relationship be? That would also be a direct relationship. Okay. Do a practice question. And one more thing to say with PIV-NERT before I talk about this. We use the ideal gas law for ideal gases. So in terms of ideal gases, what are the conditions for an ideal gas in terms of pressure, volume, and temperature? Do we want high pressure, low pressure, high volume, low volume, high temperature, low temperature? When do they act as ideal gases? I like high temperature. Right? When we're trying to boil our water, do we turn the heat on or off? We turn it on, right? Because the faster the molecules are moving, the faster they're going to escape into the gaseous phase. So at higher temperatures, they act more like gases. If we wanted to compact something, is if we have a large volume, right, and we're going to bring it down to a smaller volume, are our molecules going to be closer or farther away from each other? They're going to be closer. If they're going to be closer, are they going to act more like a solid or more like a gas? More like a solid. So do you want high volume or low volume? You want high volume, right? If you think about this room, there's a lot of gases in here. They're going to act more like a gas in a space this size than if it was just contained to the desk, right? So you want high volume, allowing them to spread out a whole bunch, and then that decreases their attraction between the molecules. And so what do we think about pressure? Low pressure, yep. Right, same thing if we were to contain it to a small container, there's going to be a lot of pressure because they're going to be moving back and forth and hitting the size of the container a lot faster. But again, if we expand it to this room, there's a lot of distance to travel before they hit the sides of the wall, creating a lower pressure, and they're going to act more like a gas that way. Okay, so these are ideal conditions for gases. The ideal gas law also talks about a specific condition, right? We're looking at one instance where we know the pressure, we know the temperature, we know the volume. We're not changing between having a large volume and decreasing it to a smaller volume, right? It's just one instant, one state in terms of the ideal gas law. So if you see anything about change, right, you're probably going to look at the relationship. But if you have a specific state, then you're going to be asked about an ideal gas. Okay. Bless you. Alrighty, so we have a gas has a pressure of 1.25 ATM at 25 degrees Celsius in a 0.5 liter container. What is the pressure if the volume increases to 1 liter and the temperature is heated to 100 degrees Celsius? Yeah. Yep, so if you're not given any information about another variable, then you can assume that that is constant. So here moles would be the same. Do you want to try this on your own or work through it together? On your own? Okay, I'll give you a couple minutes. I'll do it myself. Mm-hmm, 273.15. Did we get a pressure? What did we get?
0.7.
You got what?
0.78.
Did anyone get anything different? Okay, let's go through it. So what equation did we use here? Yep. Perfect. All right, so we have P1 V1 over T1 equals P2 V2 over T2. Yep.
That the moles are.
Yep, so if you're not given anything about the other variable, you can assume it's constant. That'll cancel out. Okay, what do we plug in for P1? Yep, we have 1.25. What do we plug in for volume? 0.5. And we'll plug in for temperature. Perfect. And then what's pressure two? What we're solving for. What's volume two? 1. And what's temperature two? Perfect. Okay. And we get x is equal to 0.782. Yeah. Questions on combined gas law? Right, we can find this based off of Pivner, right? We can look back here. P1V1 over N1T1 is equal to R, right? So we did that. Moles are constant. That's going to cancel out. Right. The combined gas law is also just P1V1 over T1 is equal to P2V2 over T2. But that is variables changing.
We'll be given the conversion rates on South Street.
Yeah, that one you'll be given. Okay, so we have a gas has a pressure of 787 millimeters of mercury at 35 degrees Celsius. And 3.125 moles occupy the system. What volume does the gas occupy? Your conversion is 760 millimeters of mercury is equal to 1 ATM. Let's try this one. Give you a couple minutes.
per building?
Let's do liters.
But it outputs it in liters.
It outputs it in liters, yes.
Are we gonna be able to do some sort of like this too?
Yep, we'll do that. We're gonna do one more gas problem and then we'll do a stoichiometry problem.
That's from partial pressure.
Someone asked for that, so we're gonna do that next.
What's the difference in this problem? What is the base problem, the temperature or the?
I would probably go based off of the temperature, and that would be 2, but we can give it in 3, that's fine. Yeah. Did we get a volume? $76.3 and what volume? Liters, awesome. Okay, so for this one, we have PV is equal to nRT, right? Different from the last question. We're using one state, we're given moles, pressure and temperature. So we're just missing that volume component. We're taking a snapshot of what that gas looks like in that moment. Right, we're not changing it and seeing what happens to it. How do we plug in our pressure? Perfect, right? So we do need to change our 787 millimeters of mercury into atmospheres. It's like 1.035, I believe. And then we can use that in our ideal gas law. So we have our pressure. We don't know our volume. We know our moles is 3.125. We know our gas constant is liters times ATM over mole times Kelvin, right? So that's why our volume is given in liters, because that's going to be the only version or only unit that's left after we plug everything in. And what temperature do we have? 30. Yep. Okay, and so volume will equal 76.13. Nope, 76.3 liters. If you have a fancy calculator, you can use the fraction button. If you have a calculator like mine, I suggest doing all of the right-hand side, dividing by your pressure.
Oh, I see.
You good? Okay. You might just be missing a 0.
Yeah.
Yeah. Alrighty, questions on Pivner? Okay, I'm just gonna give you a couple of where we can go with Pivner. So when we have PV is equal to nRT, you do have this N component, which is your moles. Couple things we can have from moles is our molar mass, which is in grams per mole. So if you're given grams, right, you can use the molar mass in order to convert to moles, and then you can plug that into the gas equation. Right, so if you start off with 26 grams of oxygen, right, you can use oxygen's molar mass to convert to moles. Right, this can be something that's produced from a limiting reagent question. You can produce a number of moles or produce a number of grams from a limiting reagent question. Right, so you have to solve for the limiting reagent first, and then that gaseous product is now plugged into your PV is equal to nRT equation. And you can also be given density is mass over volume. Right, so then you can have your volume and your grams, and you use your molar mass to get to moles, and then you have your volume component. You can switch that out for density. prove to yourself that that works. I'll have a couple of practice problems using those like slightly harder ones. But I don't think you'll be asked that on the exam. Yep.
Sorry, teacher, you're saying like we can use this and or use like one of those to get to each other?
Yes, so right, if you're given density, you can get to Pivnert, right? If they're saying, oh, this thing has a density of whatever grams per liter. You can use that in Pivnert eventually, you just have to do a little bit of conversion, right? You can eventually plug that in for N. If you're given a limiting reagent question and the limiting reagent you're solving for, or the product that you're solving for produces a certain number of gaseous product, then you can use that volume or that grams or moles of gaseous product produced into Pivnert. And then if you're given a molar mass, right, you can use your grams per mole in order to get to moles and then plug that into Pivnert. That's what I mean by all of those options. Right, so if you're like, I'm not given moles, you might be able to solve for it someplace else.
So what is it, production from what point?
Limiting reagent LR. Yep. Any other questions? Okay. So then the next thing we can talk about with gases is partial pressure. What I want you to remember here is that the sum of the parts equals the whole. And there's two things that you can do with partial pressure. One of them is you have your pressure total and the sum of all of your other pressures will equal your total pressure.
For those who have lecture tomorrow, we haven't learned this yet, right?
Yep. Okay, so if you're given something where you have pressures of oxygen, pressures of nitrogen, and pressures of hydrogen, right? Those will all have a specific pressure that you're looking for, and that'll equal the total pressure of the system. It's pressure of oxygen, pressure of nitrogen, or pressure of hydrogen. Yep. The other thing that you know is that if you take your pressure and divide it, right, your pressure of A divided by the total pressure, this is going to be equal to what we call a mole fraction, which is a fancy X. And this is equal to the number of moles of A divided by the total moles in the system. So if you have 5 total moles and 2 moles of oxygen make up that total moles, then you can say you have 2 divided by 5. So the partial pressure of oxygen is 2/5.
That's what the X represents. Partial pressure.
Yep. No. This represents mole fraction, which can either be shown as pressure of that gas divided by total pressure, or by the total number of moles of that gas divided by the total number of moles in that system.
It's just.
It gives you a value. Yep. This gives you a decimal, and your mole fraction will always be greater than 0, but less than 1. I guess less than or equal to 1. There's only 1 in the system. And the sum of all of your mole fractions has to equal 1. Yep.
So like a portion of the pressure that comes from base specifically.
Mhm.
Okay.
Right, so as an example. Any other questions before we do an example? Right, so we have a sample of gas composed of 1.5 moles of oxygen, 4.5 moles of hydrogen, and 2.5 moles of nitrogen. And I want to know what the partial pressure of oxygen is if the total pressure is 3 atmospheres. So of our 2 equations above, which one we're going to use?
Partial, mole fraction.
Yep, we're going to use our mole fraction here, right? We're given moles, but asked about partial pressure. What relates that is our mole fraction.
Is there a
I don't, yes, does it matter? No. Yeah, yeah, you'll be given both of these, I believe.
Do you know any equation we?
Um, I think you're gonna be given what you're needed.
For everything?
Yeah.
This.
For everything, really. I don't really know if there's any equations you need to memorize, TBH. I think more often than not, if you need it, they're gonna give it to you. Yeah. Yeah, they'll give you the reference sheet on the mock quiz so you can see what is given to you. And I would recommend just printing that out now, and then you can have that. I don't think they give it to it yet, but like once they post it, then print it out. Alrighty, so we're gonna be using the mole fraction here. What do we need to do first in order to use our mole fraction? We kind of have to add them all up. We need the total moles of our system. So NT is going to be 1.5 plus 4.5 plus 2.5. Mental math is 8.5 moles total. So how do we set up our equation? So we have our moles of oxygen over our total moles. And what does that equal?
It's a mole fraction.
That's mole fraction, but what does mole fraction also equal?
Yeah.
Over your pressure, right? So you can say that your pressure of oxygen is equal to your total pressure. Right, you can skip the whole mole fraction middle step portion, right? You can just jump straight to this. What do you pull or plug in for moles of oxygen? 1.5. What do you plug in for total moles? 8.5. What do you plug in for pressure of oxygen? Yep. X and then 3. So what does X equal?
It's point,
Yep. Units?
ATM.
Yep, atmospheres, right? So we have 0.53 atmospheres as oxygen. what if I asked you to solve for the pressure of hydrogen?
Be the same process, but you would use nitrogen.
Perfect, right? So we do the same thing, but instead of using 1.5, we would use 4.5 in terms of our number of moles. How would you be able to solve for the partial pressure of nitrogen if we knew our pressure of hydrogen? You could do 2.5, right? So we're gonna do moles of hydrogen. Okay, that would be our pressure of hydrogen. So we could do the same thing for our nitrogen, or we could use that first equation. We could say that total pressure is equal to the pressure of oxygen plus the pressure of nitrogen or hydrogen plus the pressure of nitrogen. And we can add up and solve for it this way as well. Okay, so there's two ways you could solve for it once you have the other two. Looking at our partial pressures, do those make sense in terms of our answers? See some head shakes, yes. Why does it make sense? What do you mean they're proportional?
Like the fraction. So like, it's all about half like of the number of moles, so the pressure in the whole system should be about half.
Perfect, right? So if we're looking at how many moles we have in our system, we know that we have the most hydrogen in the gas sample. So that means that our partial pressure should be made up the most by that hydrogen sample. You see that's about half, a little more than half is going to be made up from hydrogen. And then we had the least number of oxygen atoms, and so, or least number of moles of oxygen, so that should be our lowest pressure. And then your nitrogen should be your middle. And if we look at that, that does match up with all the partial pressures that we're getting. Okay, make sure they all add up to 3 at the very end, and then that's a good way to check your answer. Yes. Your mole fraction, or that X there, should equal 1, but we skipped the middle step of solving for mole fraction and just used the relationship that pressure is related to the number of moles. If you wanted to find mole fraction, you could do that. And you could say that 1.5 divided by 8.5. And this is 0.176. And you could do that for all 3 of them. And then that value there, this one, those would all add up to 1. Does that you see the difference between the two?
They ask for that as opposed to.
Sometimes, yeah. Yep, they could ask for that instead. You could be given the mole fraction and then you have to solve for a number of moles or something, right? And then you would have an X in here somewhere. Other questions? Do you feel better about gases? Yeah, does that make sense for partial pressures as just like a brief introduction to them? Yes, okay. They're not too bad once you start working with them. Okay, and then we wanted to see some stoichiometry problems. What kind of stoichiometry in terms of?
Whatever was on the quiz.
Yeah, or
I don't know what was on the quiz.
I think there was some like stoichiometry and molarity questions.
Okay, we can do that. Yeah. Yep. So the units don't matter as long as the units are all the same, right? If you're given partial pressures of oxygen atmospheres, and this one in millimeters of mercury, and this one's in kilopascals. Make sure they all are the same unit before you start comparing them. Yep.
Yeah. Yeah. I might
Whatever. I use all that.
First thing I had. You guys see this, okay,
Because upward bound to get a group set of students from there, we should like just watch it, you know, and then Oh, yeah, no, I don't. I know, I don't do that. Oh.
Wait, no.
Yep.
Sometimes in class, like the eye clicker kicks me out and says my location's off. Does that matter?
Are you on your phone or on your computer?
Sometimes I miss some of the questions, like the answer ability.
You probably will not matter in the end. There's a lot of points available through clickers. You're in Bengali. Yeah. So at the end of the day, like each clicker you do in class is worth like 0.2, like, or 0.8 points out of 100. So it'll work out. And you have like 130 available points or something. So if you miss a couple, it should be okay. Yeah. But then I wouldn't do that. But I also recommend just using your phone for your iClicker. It just has better location services and won't kick you out as often or ever, I think.
Do you think we'll just wait till like change those payments to like the end of the semester pretty much?
Yeah, so I go in and grade them every week. And then I have to sync them to Canvas. And the attendance is not linked to the polling, right? That's like two separate things. So if you have an excused absence, then I don't know how to sync those yet because I am just a girl. But I need to update last week's to sync it to last week's stuff. Yeah.
No, I'm not, I just like, I didn't even think that they were, because I swear mine have been stayed the same, but.
Yeah, and it might be, right, at the end of the day, there's still a lot of points. So if you miss a couple questions, it's not gonna like totally affect your grade. The eye clickers are there to be helpful to you. Oh boy. And if you miss a day, that's not gonna like kill your grade, make you go from an A to a B. Honestly, it's gonna be very, very, unseen really in terms of it. It's just supposed to be 100 points for your grade. Yeah. I didn't read that part of the syllabus, so I can't speak on it. So I don't know, but Again, just a girl. Figure it out. I figured out Canvas at one point. I'll figure out this one too. I just need a weekend.
I don't know.
Alrighty. So here is a solution stoichiometry question. For this one, we have how many milliliters of 1.5 molar nitric acid is required to react with 100 grams of copperous oxide? We're given our equation. What do we need to do first? Nope.
You gotta convert the.
Nope.
balance.
We have to make sure it's balanced. I will drive that into your head the rest of the semester. The first thing you do is going to say, is this balanced? I don't care if the question tells you you have a balanced equation. You need to make sure that it is balanced.
So you can't.
Um,
Are you saying they're gonna get you on that?
They might you might read the question and it will say, oh, according to this unbalanced reaction, but you might read it as balanced and then you'll just start going. Like, I want you to always, or you might say it's balanced and then it might not be, right? They might have just dropped a number. So just make sure that something is balanced before you start, or they're just gonna give you an equation and not tell you if it's balanced or unbalanced, and you have to make sure it's balanced. So just make sure it's balanced, please. Many students have lost points over the years that I've been grading because they did not balance their equations. So I will save you now. Is this one balanced? Yes, it is. Okay. So now what's the next thing we have to do? Yep, so we're looking for how many milliliters of nitric acid, and we're giving to that in concentration. What is capital M? Capital M is molarity, which is moles over liters. So we're looking for that liter component.
So I feel the copper and the NO3, we didn't split that up. That's because the NO3 is that non-soluble.
So both of these I think would be soluble in solution. Actually, the nitric acid would be soluble. I think the copper oxide might not be. But it doesn't, you only split that up if you're looking at the net ionic equation. Here, we're just given the chemical reaction and we don't split those up in the chemical reaction. Here or?
Yeah.
Those are their products. So after your reaction happens, that's what's produced. You get copper nitrate, nitric acid, NO, whatever that is. It's a gas, and then water, right? So whenever this reaction happens when those two combine, produces those things. That's why they split up. Okay, so we know that, yeah. For this case, no. Yeah. The only time you would have to predict your products is if they're just switching partners. Yep. So if you go from two reactants to two products. I don't think there's anything that's 3 that you're required to know. But yeah, 2 to 2 is all you're required to know. Alrighty, so we know that mole or concentration is moles over liters. What else do we need to convert? Yep, we need to convert grams to what? We need moles, right? The whole point of this question is saying, how much of my nitric acid do I need to have to completely react with my 100 grams of copperous oxide? So we have 100 grams of Cu2O. I don't know what that is. This could technically be related to limiting reagent. In this case, we're asking for how much is required to react with this much. And so we're saying we want 1-to-1, or we want stoichiometric equivalence, right? So all of both reactants get used up. So this is going to be 1 mole of Cu2O is 143.1 grams. Where can we go once we have moles of copperous oxide? We can use our mole ratio, right? So what's gonna be our mole ratio we're using here? So we have 14 moles of HNO3 is equal to 3 moles of Cu2O. Right, we're saying we're using both reactants up completely. So we want all of our 100 grams of Cu2O to be reacted with all of the nitric acid we're going to be adding to our solution. How do we get to milliliters from moles? Yep, we can use our molarity. What's our molarity? 1.5. Where does 1.5 go? On the bottom, right? We have 14 moles up top. So in order to cancel that molar unit out, we need 1.50 moles per 1 liter of solution. And how do we get to milliliters? 1,000. Yep. So 1 liter is equal to 1,000 milliliters. Sorry, that got tiny. You get 2.174 liters times 1,000 is 2,174 milliliters. Or you can say this is 2.17 times 10 to the 3.
Both of the 1.5 moles to the 1 liter.
Yep, so your concentration is given right here at 1.5 molarity. So that is 1.50 moles over liter.
Oh,
So in order to cancel out the moles, we just need to flip that value. Yep. Any questions on this bad boy? Just make a little bit more sense in terms of like solutions and how you're using it. Yes,
But it's 1.5 moles, not 1.5 layers.
what do you mean?
Like 1.5 M, that's it's 1.5 moles per liter. So
Yes.
you're looking at-
Yep, so that's like saying 1.50 moles divided by 1 liter is the same thing as 1.50 capital M. Yep. Any other questions on solution stoichiometry? Yeah. Yeah, if it doesn't necessarily matter for that question, they might not include it. But more often than not, it'll be where it's supposed to be. I'm just, for right now, I just didn't include them. But like, because we know that the nitric acid or HNO3 is a solution, that would say aqueous next to it, right? We have 100 grams, that's probably going to be a solid in terms of your reactants. And then you're putting that into solution. So we know that nitrates are always going to be soluble. So that copper nitrate is going to be soluble afterwards. Water is going to be your liquid. So that would be a liquid. And then I believe the NO is a gas. So you can kind of figure that out from there too. Okay, any other questions? I think I have a couple of these examples on last week's practice problems, but I'll make sure that I include 1 or 2 of them in this week's as well. Yeah. I usually base my significant figures off of what is given in my question. So we're given two values, we're given 1.50 and we're given 100. 1.50 has 3 sig figs and then 100 has 4. So I go off of 3. Anything else? Is there anything else you would like to see from me before the exam next week?
But if this comes out, can we go over some of that?
Mhm.
That's next week or whatever. it
Yeah,
is.
absolutely. We can do, right, if you come to on Tuesday to that Zoom review, then we can kind of go over some things there. And then I believe this weekend they'll release both of the mock exams, and so I'll have both of those done by Tuesday as well.
That's the same. Could you also maybe touch on like the acid and base stuff?
The titrations and stuff, yep,
Yes.
yep, absolutely. Yep.
Kind of just like what you would study for if you were to take this exam.
Yep, so I can tell you that right now, since you still have a week. So I would go back and look at your homework. Once your quiz comes out, I would look at your quiz 1 and quiz 2, and I would say, what did I get wrong? And analyze with the fine tooth comb what happened, right, in those questions. Was it because you didn't understand the problem? Was it because you made a silly calculator mistake? Or was it because you just like something else? And I would take those and I would look back at a homework question then and find those topics and kind of review your homeworks that way. And then I would go through your chapter notes and any practice problems that you did or didn't do in class. I would make sure you know how to do those, because I think those are pretty reflective of stuff you'll see on the exam as well. Question? Okay. And then in other terms of things that I would study, I would just keep practicing as much as possible. If you're like, I really don't understand stoichiometry. If you look up stoichiometry, chemistry, practice problems, worksheet on Google, like a whole bunch pop up, sometimes usually with an answer key. So you can kind of practice there. I think the more you read chemistry problems and the more you look at chemistry problems, the easier it is to identify what you have to do. So definitely do your mock exam, definitely look over your quizzes, and then look back at any old homeworks or in-class practice problems. Yep. Yes, yep.
Mock exam?
There's one mock exam, but I will be covering both Dr. Altimos and Dr. Bengali, so you technically get to see two. Unless they give me the same mock exam, yeah. Yep. Yeah, your exam is in class, like when you would usually go to class on Thursday or Friday. Yep, they'll be posted on campus. Probably Friday or over the weekend. Yep.
Thank you. Have a great day.
Yeah, thanks so much, y'all. Thanks for coming. Thank you.